Welcome to Quantum Computing Lecture 5. We will be discussing a little history lesson in this lecture about classical automata theory, the foundations of computational models, why these are needed. Once we'll be through with this lecture, we will look into lecture 6, the quantum automata theory, in more depth. We will look at what is automata theory, why study automata theory, because computer science or computing is not limited to classical binary computing. Quantum compute is also computer science. What is finite automata? What are regular languages, pushed out automata, Turing machines, practical applications, why should we care? We will have more focus on the use of automata because that's where we are going to expand upon in our quantum computing learning. What is automata theory? The study of abstract machines and problems they can solve. The core concepts are models of computation such as finite automata, push-down automata, Turing machines, formal languages and grammars, compatibility and complexity. The goal here is to understand the limits and capabilities of computational systems, and this is classical computing or classical computational systems we are discussing in this lecture. Why study automata theory? The theoretical foundations of computer science based on automata theory, basis for computer science algorithms and programming languages. In quantum computing, we will be using algorithms and programming languages. Practical applications are compiler design, artificial intelligence, cryptography, and hardware design. And quantum cryptography is an area, whereas quantum application and artificial intelligence is another area that we'll be looking in quite depth. Problem solving helps model real-world systems such as vending machines, traffic lights. Now let's look into vending machine automata, how it works in a story fashion to understand it in more depth. David had always been fascinated by how machines seems to make decisions on their own. Remember, this is classical computational theory. One afternoon, while waiting for his bus after school, he noticed a soda vending machine at the bus stop was not working properly. Instead of dispensing a drink after inserting coins and pressing a button, it would sometimes get stuck or flash an error. Curious, David remembered his computer science teacher, Miss Thompson, explaining how machines like these could be understood using something like deterministic finite automaton or DFA. It has limited or deterministic finite states. He wondered if the machine's confusion was because its internal rule book was messed up. David decided to take a closer look, imagining the vending machine as a simple system with clear states and transitions, just like examples they discussed in the class, in their computer science class. The next day, David sketched out a DFA for the vending machine. During his study period, he identified three key states: waiting for coin, coin inserted, and dispensing drink. The transition were straightforward. Inserting a coin moved to machine from waiting for coin to coin inserted, and pressing a button in the coin inserted state triggered the dispensing drinks state. If the machine did not follow these steps in order, it would get confused, just like a bus stop vending machine. David realized that the machine's problem might be a glitch in how it was following its own rules. He even drew a diagram in his notebook, like we do our activities in class activity, labeling each state and the inputs that caused the machines to switch from one state to another. Feeling a thrill as the pieces started to make sense. Excited by his discovery, David shared his diagram with Miss Thompson, who was his computer science teacher. She was impressed and encouraged him to think about how deterministic finite automatons were everywhere from traffic lights to elevator buttons. You just have figured out how to model a real world problem using a theory, she mentioned. David grinned, realizing that understanding DFAs was not just about passing a test. It was about seeing the hidden logic in every machine or everyday machines. That weekend, he had even tried explaining it to his little sister using board game as an analogy, showing her how each move was like a transition in a DFA. For David, the vending machine was no longer just a box of sodas. It was a puzzle he could solve with the right rules. I deliberately shared this use case so you can paint a picture in your mind how three states work: waiting for coin inserted, dispensing the drink. Finite automata is simplest model processes input symbol by symbol. The types are deterministic finite state automata or non-deterministic finite state automata. The examples are password validation, the such as must start with a letter and end with a number. Let's jump into this example to understand in a little bit more depth. Imagine you are designing a simple password system for a new application or an app, and you want to make sure every password follows a basic rule. It must start with a letter and end with a number. To build this, you need a way to check each character of the password one by one and decide whether it meets the criteria. This is where deterministic finite state automaton or DFA comes in. A DFA is like a flowchart or a rule book for a machine. It tells the machine exactly what to do at each step based on the input it receives. In this case, the machine is your password validator, and the DFA defines the rules it follows. For example, the DFA starts in an initial state waiting for the first character. If the first character is a letter, it moves to the next state. If not, it rejects the password immediately. It's a step-by-step process with no surprises, which is why it is called deterministic. Every input leads to exactly one step. Let's break it down with the password example in more depth. Your DFA has three states: start, middle, and end. It begins with the start state where it expects the first character to be a letter. If you type a letter, it transitions to the middle state where it accepts any combination of letters or numbers. However, if the last character is not a number, the DFA won't transition to the end state and the password is rejected. Think of it like a vending machine as mentioned earlier. If you don't insert a coin first, it won't give you the soda, no matter what buttons you press. Similarly, if the password does not follow the sequence of rules, letter first, number last, the DFA won't accept it. This makes DFAs incredibly useful for tasks like validation, where you need to enforce strict rules in a predictable way. The power of DFA lies in its simplicity and precision. It does not remember the entire password. It only cares about the current state and the next input. For your password validator, the DFA ensures that every password is checked efficiently without complex calculations or memory. This is why DFAs are used in everything from text processing to compiler design. They are like the traffic cops of computing. They don't overthink, they just follow the rules and direct the flow based on what they see at each step. So the next time you create a password, remember that a DFA might be working behind the scenes, quietly making sure your impact as an input that you're giving fits the pattern. Regular languages. The definition is regular languages recognized by finite automata. Applications, text search, grep command, lexical analysis in compilers, the email validation using regular expressions, and the regular expressions are given here. What are regular languages? Let's look into this in our continuing example of password. Imagine you're building a program to validate user inputs like passwords, as mentioned earlier, or email addresses for a new app you're developing. And continue with David. David already knows how a deterministic finite automaton can help enforce simple rules, such as ensuring a password starts with a letter and ends with a number. What if you want to add more flexibility in this, like permitting passwords of varying lengths or requiring at least one special character? This is where the concept of regular languages come into play. A regular language is essentially a set of strings, like all valid passwords, that follow specific patterns or rules. These patterns can be described using tools like regular expressions or represented by machines like DFAs or NFAs. Non-deterministic finite automaton is also known as NFAs. For example, the regular language for your password rules might include strings like Apple 123. Apple's A is caps, or secure P @ SS1, where secure's S is capital, but excludes 123 password because 123 password does not start with a letter. Or no numbers here, capital N, small o, capital N, UMBERS, capital HERE. The key idea is that if you can define the rules clearly, a machine can use them to quickly check whether any given input is valid or not. For you, as someone knowingly working in tech or computer science, regular languages are incredibly practical. They are used in almost every system that processes text, from validating user inputs in web forms to searching for specific patterns in language datasets. For instance, when you are designing a login system for your workspace, you might use a regular language to ensure that your email address entered follows a standard format. Similarly, if you are parsing log files or configuring a server, regular languages allow you to filter and extract the exact information you need efficiently. Tools like grep, GREP, or SED, and even programming languages like Python rely on regular expressions, shorthand for regular languages to handle these tasks. Without them, you would have to write complex, error-prone code just to check for something as simple as correctly formatted phone numbers or IP addresses. The beauty of regular languages lies in their balance of simplicity and power. They allow you to define complex patterns in a concise way, making your code cleaner and more maintainable. So whether you're building a custom tool for your team or optimizing an existing system, mastering regular languages gives you the ability to create robust, reliable solutions that handle real-world inputs with precision. So the next time you're setting up validation rules or debugging input errors, you will have the confidence to design systems that are both efficient and easy to understand. Now let's look into push-down automata. Let us say that we are writing a simple program and we want to make sure that our if-else blocks are written correctly. Every if statement needs to follow a specific structure. It starts with a keyword if, followed by a condition in parentheses, and then block of code wrapped in curly braces or properly indented actually. If you miss a brace or forget a parenthesis, the program might fail to be or behave in unexpected ways. This is where the concept of regular languages become useful. While they can't handle the full complexity of programming language, they can help enforce basic syntax rules. For example, a regular language can check that an if is always followed by a bracket, then a condition, and then a closing bracket, and finally a curly brace to open the code block. These rules act like a first line of defense, catching simple syntax errors before your code even runs. In most code editors and compilers, regular languages play a key role in syntax checking. So that is technically the regular language use. But what is push-down automata? Let's dive into learning the PDA. So when it comes to checking the syntax of if-else blocks, a deterministic finite automaton or regular language, as we are discussing, can handle the basic structure, like ensuring parentheses and braces are balanced and at a surface level as mentioned earlier. These tools hit their limits when dealing with nested structures such as an if block inside another if block or matching each opening brace with a corresponding closing brace. This is where push-down automata comes handy. A PDA, push-down automata, is like a DFA but with an added stack memory, which allows it to keep track of nested elements. For example, when the PDA encounters an opening brace, it pushes it onto the stack. When it later encounters a closing brace, it pops the matching brace from the stack. If the stack is empty at the end of the code block, all braces are properly matched. This capability makes PDAs perfect for validating the correct nesting of if-else statements, loops, and function calls, tasks that are beyond the scope of regular language. Push-down automata are especially useful in compiler design and syntax analysis, where they help parse the hierarchical structure of programming languages. For instance, a PDA can ensure that every if statement is correctly paired with its else if present, and that all code blocks are properly closed even if they are nested multiple layers deep. This is why PDAs are a fundamental part of tools that analyze and compile your code. They bridge the gap between simple pattern matching handled by DFAs and more complex grammar rules required for programming languages, making them essential for building robust and reliable software. Since you are all computer science folks, I'm pretty much sure that you have heard what Turing machines are. The definition is theoretical model of general computation. The significance is defines computable problems. The basis for the Church-Turing thesis. The example is modeling algorithms for unsolvable problems such as halting problem. I will not go in much depth in Turing machines, however, I'll share with you an example that will allow you to expand your comprehension. A Turing machine is often described as most powerful model of computation, capable of simulating any algorithm or computer program, no matter how complex. Imagine a machine with an infinitely long tape divided into cells, a read-write head that moves left to right, and a set of rules or states that tell it what to do based on what it reads from the tape. If you don't know what tape is, go search on the Google in Turing machine's context. Unlike deterministic finite state automaton or the push-down automatas, which are limited to specific types of languages. A Turing machine can recognize any computable program or problem, meaning if a problem can be solved by a computer, a Turing machine can solve it too. This makes it a foundational concept in computer science, especially in understanding the limits of what computers can and can't do. For example, it can simulate everything from simple arithmetic to complex programming language logic, making it a universal model for computation. Turing machines also play a critical role in defining the boundaries of computation. They help us explore questions like what problems can be solved by computers, a field known as computability theory. For instance, the famous halting problem, as mentioned on the slide here, which asks whether a program will run forever or eventually stop, was proven unsolvable using Turing machines. While they are mostly a theoretical tool, their principles underpin how modern computers and programming languages are designed. Understanding Turing machines gives you insight into the very essence of computation, from the algorithm powering your apps to the fundamental limits of what technology can achieve. The practical applications here are compiler design, where lexical analysis or regular expressions are used, syntax parsing or push-down automata, AI and robotics, state machines for decision making, network protocols, finite automata for packet routing. So I would suggest you to conduct a little research on these areas, going on Google Scholar or IEEE Explore to find papers what other people have already published in this area. Why should we care? The bridging theory and practice helps design efficient systems in classical computing. We are not discussing quantum at this moment, quantum computing at the moment. Innovation foundational for quantum computing and bioinformatics and other fields. Career relevance essential for software engineers, data scientists, and researchers. So, introduction to automata, as we discussed earlier, here I have added some of the examples that I thought relevant for you to look into. This is an abstract mathematical model of computation that processes sequential input, fundamental building blocks for understanding computational theory and language processing. The Q0 is our start state and Q1 is our next state. Input goes from Q0 to Q1. It consists of states, transitions, input, alphabet, and acceptance criteria used to design compilers, text editors, network protocols, and hardware circuits. The image here is explaining the basic idea of a finite automaton, which is a simple model used in computer science to design systems that follow specific rules. Think of it as a machine with different states, like different stages in a process, and set of instructions for moving from one state to another based on the input it receives. For example, imagine a turnstile at a subway station. It starts in a locked state, and when you insert a coin, the input, it transitions to an unlocked state, permitting you to pass through. The machine also has the input alphabet, which is just a list of possible inputs it can recognize, like coins or buttons. Finally, it has rules for deciding whether an input is accepted or rejected, such as only permitting entry after a coin is inserted. So if you are in USA and you're using a Canadian quarter, machine will reject it and you'll get that quarter back. But if you use the standard US quarter, the machine will accept it and let you through to the subway. Finite automata are incredibly useful in designing tools and systems we use every day. For instance, they help create compilers, which are programs that translate the code you write into a language the computer can understand. When you write a line of code, a compiler uses rules defined by finite automata to check for syntax errors, like missing semicolons or unmatched brackets. They are also used in text editors to provide features like auto-completion or highlighting errors in real time. Even network protocols, which grown how data is transmitted over the internet, and hardware circuits like those in your smartphone or computer rely on finite automata to ensure everything operates smoothly and predictably. So let us take a real life example, the vending machine which I shared with you. The machine starts in an idle state, waiting for you to insert money. When you insert a dollar bill, the input, it transitions to a ready state where it waits for you to select a snack. Once you press the button for your chosen snack, it moves to a dispensing state and releases your item. If everything goes correctly and you have not inserted a Canadian bill instead of a US bill, it returns to the idle state, ready for the next customer. The vending machine's behavior is defined by its states. The inputs it accepts money and the button presses, and the rules for transitioning between states. This is exactly how finite automata work, making them a fundamental concept for designing reliable and efficient systems. Simplest form of automaton with exactly one transition per state symbol pairs start 0 or 1, accept or reject. Example, binary string ends in 1. Formally defined as a 5 tuple. The Q are the states, the sigma are, the bringing in, what you are bringing in. The big sigma. The small sigma is the transition. The Q0 is the first state, F is the final state. Representing states, alphabet. Sigma is also the capital sigma, not the small sigma. Capital sigma is the alphabet. Transitions are the small sigma. Start and accept states are the Q0 as the start state and F is the final state. Recognizes exactly the class of regular languages with deterministic state transitions. Every DFA has exactly one computation path for any given input string. Non-deterministic finite automaton. Now let's look into this with an example. The image given here is describing a non-deterministic finite automaton, or NFA, which is more flexible version of finite automaton. Unlike a regular finite automaton, an NFA allows for multiple transitions from the same state for the same input symbol. This means that if you are in the state Q0 and you receive a specific input, the machine can transition to multiple states like both Q1 and Q2 at the same time. Additionally, NFAs can have something called epsilon transitions, which let the machine change states without consuming any input. Remember, this is still classical computing. We are not discussing quantum computing here. Think of it as like a standing at a crossroads where you can choose multiple paths or even move forward without taking a step, exploring all possible directions simultaneously. The key advantage of an NFA is its ability to be in multiple states at once, permitting it to explore all possible computation paths in parallel. For example, imagine you're designing a search feature for a text editor. An NFA can efficiently handle patterns where there are multiple valid continuations, like searching for words that might have optional letters or varying spellings. Instead of following one path at a time, the NFA can branch out and explore all possibilities, making it very powerful for tasks like pattern matching and text processing. Let's say you are designing a simple system to recognize the words cat and car. An NFA could start at Q0 and, upon seeing the letter C, transition to multiple states that represent the possible next letter A for both words. After reading A, it can then split again to check for T or R. This way, the NFA can efficiently recognize both words without needing separate machines for each possibility. NFAs are widely used in areas like compiler design, search algorithms, and even artificial intelligence, where flexibility and parallel exploration are crucial. Equivalent power to DFA in this multiple path possible, whereas every NFA can be converted to an equivalent DFA, or often simpler and more intuitive to design, but requires exponential state explosion when converting to DFA. We will be looking at quantum state explosion later in our upcoming weeks. Computational complexity in standard classical computing studies resources, time, space required by automata to solve problems of given size. P is a class contains problems solvable in polynomial time. NP contains problems verifiable in polynomial time. P versus NP is the central unsolved question. Can every efficiently verifiable problem can be efficiently solved? Now that's a great question for you to conduct research on. NP complete problems are hardest in NP. If anyone has polynomial solution, then P is equal to NP, where P belongs to NP technically. The key takeaways: automata theory models computation applications span software, hardware, and artificial intelligence. Call to action is explore further. The books are Spicer's Introduction to Theory of Computation. However, before I close the lecture, I would like to bring in a little bit quantum computing in this, so you can understand why we need DFA, NFA, and PDA, and regular expressions and languages for quantum computing. The journey from classical automata like DFA, NFA, regular languages, and PDA to quantum automata is like building a foundation before constructing a skyscraper. Each type of automaton teaches us essential concepts about how machines process information, make decisions, and handle complexity. For example, a DFA helps us understand deterministic behavior, where every input leads to exactly one outcome, while an NFA introduces the idea of parallel possibilities, permitting a machine to explore multiple paths at once. Regular languages give us the tools to define patterns and rules like validating user inputs or searching text, while PDAs or push-down automatas add memory with a stack, enabling us to handle nested structures like loops or function calls in programming. These concepts are crucial because quantum automata build on them, but instead of classical bits 0 and 1, they use quantum bits or qubits, which can exist in multiple states simultaneously. Without mastering the basics, it would be impossible to grasp how quantum automata leverages superposition and entanglement to process information in ways that classical machines cannot. Let us consider a real-world example: searching a database. A classical automaton like a DFA or NFA would search through the database one entry at a time, following a set of rules to find a match. A push-down automata could handle more complex queries by using a stack to keep the track of nested conditions, like searching for records that meet multiple criteria. But a quantum automaton could search the entire database at once by leveraging superposition, exploring all possible answers simultaneously, and collapsing to the correct result only when measured. This is similar to how an NFA explores multiple paths, but quantum automata do it exponentially faster due to the nature of qubits. For instance, if you are searching for a specific record in a massive dataset, a quantum automaton could find it in a fraction of time it would take a classical machine, revolutionizing fields like cryptography, artificial intelligence, and big data analysis. Let's conclude this lecture that the transition to quantum automata is not just about speed, it is about re-imaging what computation can achieve. Classical automata teaches us how to structure problems, define rules, and manage memory, but they are limited by the sequential or parallel, yet still finite nature of classical computing. Quantum automata, however, open the door to solving problems that are currently intractable, like simulating complex molecular interactions for drug discovery or optimizing massive logistical networks in real time. By starting with DFA, NFA, regular languages, and PDA, we develop the intuition needed to understand how quantum automata can break through classical limits. They represent the next leap forward, where the rules of quantum mechanics, superposition, entanglement, and interference allow us to tackle challenges these were once thought impossible.